The next topic that we'll review here is some other factors that may affect entropy. We looked at temperature and phase. So just to review here, when gases are formed from liquids and solids, so we're going from either gas to liquid or gas directly to solid, these would both be indications of an increase in entropy. When liquids are formed from solids, so the other phase change that we didn't mention there, liquid to solid, that would also imply a change in entropy. And then if the number of gas molecules increases, we would also say that that's an increase in entropy. So what we see here are our two reaction flasks. So this one's sealed, and inside we have 2 moles of NO, 1 mole of O2. And this is the equation over here that is referenced in these two reaction flasks. And then we see on the product side here, or in this vessel here, the product side indicated, we only have 2 moles. So we went from 3 moles of gas down to just 2 moles of gas. So this would actually be a negative entropy change. So we could say that this would be a negative delta S for this scenario here. So let's take a look at sample exercise 3 and later 4 here, and we'll see if we can determine whether each of these processes would produce an increase or decrease in entropy of our system. So let's look at example A here. So what we see is a change in phase. So first, look for any changes. So the structure is the same. So what we can compare here is that we're going from a solid to a gas. So we mentioned in general, this would be a increase in entropy. So we'll say this column here will be a positive delta S. This side over here, we could equate with a negative delta S, but this first example would definitely be an increase in entropy. Those molecules are definitely be more chaotic, more random in the gas phase than in solid. Let's look at example B here. We have a solid and 1 mole of gas, and then we go to a combination reaction here. So now we just have a solid. So 2 moles of something to 1 mole of something. This would definitely be a decrease in entropy. We've lost that mole of gas completely, so overall a negative delta S. Let's look at example C here. So we have HCl gas, ammonia gas, and on our product side, we have 1 mole of solid. So once again, this is definitely a decrease in entropy. The system is definitely more organized and less chaotic in the solid form now. All right, our last example for sample exercise 3, part D, we have 2 moles of SO2, 1 mole of O2. So we have 3 moles of gas on this side, and then we go to 2 moles of gas, SO3, on the product side. So once again, our last example here is also a decrease in entropy. So let's look at another way of looking at this, or not really another way, but now we're going to look at more information at one time and see what we can compare. So again, we're going to choose the system with the greater entropy now. In each of these cases. So in part A, we have these conditions. So 1 mole of H2 at STP. So if you recall, standard temperature and pressure would be 0C and 1 atmosphere. So anytime STP is referenced, these are both the same, the last two, but that's what we would consider or compare. So let's compare temperature over here, 0 to 100. So an increased temperature over here and a decreased pressure, which would imply an increase in volume. Pressure and volume are inversely related. So when you decrease pressure, so we went from 1 atmosphere to half an atmosphere, we have also increased volume. So if we want to know which conditions would have a greater entropy, we'll go with the higher temperature and the increased volume. So 1 mole and the same structure, H2, we can't compare those, right? So these are the same. So what we have to compare will be temperature and pressure. But really, the pressure we can't really think of directly. We have to kind of equate that to the inverse volume relationship. So let's look at B and we'll do the same. So we have 1 mole, 1 mole. So those are the same. So we'll not consider those. Then we have different phases. So I have solid water, so solid H2O, and then I have liquid. All right, and then the temperatures correlate with those as well. So we don't really have to look at temperature and consider that too much because we know that liquid phase is definitely more energetic, more chaotic, higher kinetic energy, and therefore higher entropy. Let's look at case C here. So we have 1 mole of each, but our compound is different. And then the rest of the conditions are the same. So I didn't really elaborate on structural differences and how they will affect entropy, but we can just quickly take a look. This is not the correct Lewis structure for SO2, but just so we can see there's a sulfur with 2 oxygen bonds versus just 2 hydrogen atoms bonded together. So this is just, again, a quick sketch just to show that this is definitely a more complex molecule and would have way many more vibrational modes, stretching, bending, wagging, all of those bonds doing different things at different times. So the conditions of the larger compound with more bonds would definitely be more chaotic, more higher entropy. All right, our last scenario here. So again, let's compare. STP is the same, so we'll cancel that out. We won't consider that. So I have slightly different structures, but in this case, the sheer number, the moles are double on the right-hand side here. So you have 2 more bonds maybe on this side, but you have 6.022 times 10 to the 23rd more molecules over here. So overall, again, the right-hand side will have a higher entropy than the left-hand side. So we'll continue next time with the next topics.